Hello my test tubes and welcome to a Cambridge Chemistry Challenge preparation video. Today I'm going to be going over the 2011 Cambridge Chemistry Challenge. To get the most out of this video, I suggest you go over the paper, and then what I'm going to do is explain what the quickest thought process behind solving this Cambridge Chemistry Challenge would have been. At least I think the quickest solving process would be. I mean, you might be much better, in which case you do your own thing, guys. The more of your own thing you do, the better, I think. Anyways, for part one, one compound with formula C3H6 is obviously going to be propene, so that's propene, and that's an alkene. And then the second one, well, another double bond doesn't form an isomer. A double bond somewhere else doesn't form an isomer because they're all going to be the same, and another double bond is going to pick away another hydrogen. So we're left thinking, what can we do? Because one double bond is the only option we have for the one double bond is this. Then for two double bonds, nothing works, and for one double bond, nothing works. Sorry, for zero double bond, nothing works. Double bonds, nothing works. So we end up thinking of this, and this is cyclopropane, and that's a cycloalkane. I'm not going to write that out because it's long. For B, draw the structure of A and the product form when it reacts with bromine. So A is this, and then when it reacts with bromine, there's going to be a bromine on each side, so that's going to be Br and Br. For part C, we have just this thing reacting, and because it only forms one product, I'm fairly sure there's just going to be this bond that's going to break, or one of the bonds that's going to break. And so here we have two H's, and here we have two H's, and we need a third thing on each. So I think that there's going to be an extra bromine on each at the end. So that gives me Br zigzag, and then another Br here. Okay, part D, the equation of the complete combustion of C3H6. C3H6 plus some number of O2 gives me CO2, 3CO2 plus 3H2O, which is 3O2 plus 1.5 O2, so 9/2 O2. For part 2, I calculate the standard enthalpy change of formation of A. Well, we have 3C plus 3H2 forming A, and this is my delta H formation. Then we're also given the enthalpy changes of the combustions of each of these two. So I'm thinking 3CO2 plus 3H2O, and this enthalpy change of combustion is going to be 3 times the enthalpy change for carbon plus 3 times the enthalpy change for hydrogen. So that's going to be minus 3 times 393.5, and then minus 3 times 241.8. And then this has an enthalpy change of combustion of 2058 kilojoules mole. So the reverse process, minus 2058 kilojoules mole. So the reverse process, the arrow in this direction, is going to be 2058. So combining all of these together, summing them to give this arrow, is going to be minus 3 times 393.5 minus 3 times 241.8 plus 258, which gives me 152.1 kilojoules per mole. For this one, for part 3, the standard enthalpy change of formation of B, the only thing that differs from the formation of A is instead of the minus 2058 or plus 2058, we have a 2091, so minus 3 times 393, minus 3 times 241.8, 0.5 for the first one, plus 291, and that gives me plus 185.1 kilojoules mole. And finally for E, we have some B, and then it goes to A, and in between it can have its like original state of 3C plus 3H2. And here this reaction, the reaction from 3C plus 3H2 to A is going to be 152.1 kilojoules per mole, and then the reaction from B to the original state is going to be minus the enthalpy change of formation, so minus 185.1 kilojoules per mole. And this gives me a total enthalpy change of 152.1 minus 185.1, giving me minus 33 kilojoules per mole. For part F, giving all attachments of a single D to this compound, so all replacing of a hydrogen by a single D, we can have the D standing here and the D standing here, and also the D standing here. If you look at this option, you have to remember that the double bond does not turn, and so just like in Z, E's isomerism, this is going to be a different isomer to this one. For part 2 of F, this was part 1, we're looking at how a hydrogen, each of these has 2 hydrogens, so all the vertices are symmetrical, how one of the hydrogens can be replaced by a deuterium. And it seems that, well, you can add a deuterium to any of these vertices, but then you can turn them round to make them all the same. So actually there is only one single isomer, and it's going to be this one. Looking at G, the deuteriums are in exactly the same environment, and there are 2 of them. Well, here we can only add 1, and here, as discussed earlier, these 2 deuteriums are going to be in different environments if they're on the same one, because the bond can't rotate, so the 2 deuteriums are going to be on here, because if the 2 deuteriums were on different carbon atoms, then obviously they'd be in different environments. Then looking at what happens when A1 has a deuterium-2 molecule added to it, well, this double bond is going to break, and we're going to have deuterium, 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 and deuterium. And here I start getting confused because there's 2 different isomers, X1 and X2. So I think maybe, maybe this D, and if it was down here, would be different. But it's not, because this time it's a single bond, and a single bond can rotate. And this is definitely the only product that can happen, because, well, we know what the process is, and the process will always be this. So we have to look for another type of isomer, and then we remember that this carbon actually has 4 different groups to it. So the hydrogen can either be going out of the plane like this, or going into the plane like this. So A1, A2 and A3 also form this product on deuteration, and we've looked so far, so the product here, D somewhere here, D and D, and we've looked at the case where the double bond was here, and these 2 were the deuteriums that were added. So let's look now, as our second option, what would happen if the double bond was originally here, and these 2 were the deuteriums added. Then this deuterium and this deuterium would be there originally, and our first A2 and A3 would look something like this. And then we've looked at this, the EZ isomerism case before, so we know that it's also different from this, and this gives us the options for A2 and A3. Looking at part J, because 2 different compounds, A4 and A5, form a single compound upon deuteration, I'm inclined to believe that they're both isomers of the form D and D. And if we add we've already tried the option where the first deuterium is on this end, so the second deuterium is either going to be here or on here, and if the second deuterium is here, then there will be no 2 isomers, so I believe they're going to be D and E. So that's A4 and A5, and then Y becomes 2Ds here, D and 2Ds here, D and D. Excuse me, this is Y, this is A4, 5. We've looked at the cases where a single compound produces two different products, and that's usually from experience that we've had in part I, in the case where one of the hydrogens here is a hydrogen and one of them is deuterium, in which case there's going to be optical isomerism. So if we don't want any optical isomerism, we want there to be two deuteriums on here, so that's D. So that's a deuterium at the beginning, and we've looked at the case where we've had a deuterium at this end of the double bond, so that's already taken. So if we don't have a double bond where the deuterium is, this gives us the structure A6, and then product Z is going to be deuterium, 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 and deuterium here. I'm not going to draw the stereoisomerism because I mean you can do that, and there's no isomer stuff. For part L, I suggest just drawing out in order all the isomers that you already have, and then just looking at the one that you don't have, and the one that you don't have is this one. So that's going to be A7. For part M, I'm going to first draw out all of the isomers I can think of. This gives me, actually, because I know that each of the isomers is going to have exactly two deuteriums. I know that all three of the vertices can't take a deuterium at the same time, and so I'm going to leave the top vertex untouched all the time. So we can have two deuteriums here. So this is spaced double bond and double bond, single bond coming into the page. B. Alternatively, we can have deuterium on this side going out of the page, and on this side going into the page. D. Or a deuterium on this side going into the page, and here going out of the page. Or a deuterium here, and both of them are going into the page, into the page, yes. Or both of them are going into the page. And I think this ends our combination list out of the page. This is out of the page. However, just checking that we don't have any repetitions, if I turn this triangle around, I get this one. So I'm just going to use this triangle here, and this one's not needed anymore. And for this triangle, if I turn one of the triangles around, I don't actually get the second one. So these four are indeed my options. Now, looking at this particular case, if you rotate it by 180 degrees, you're going to get this, which is a completely different compound from a completely different looking thing than what we had originally, meaning that it does not have rotational symmetry. However, it does have plane symmetry, because this is my plane over here, like in the middle. So yeah. That means that it goes into no rotational symmetry, plane of symmetry, so this is 2. Then looking at this one, it does not have a plane of symmetry, because no matter where you put the plane in the middle here or here, if you put it here, then this side has a deuterium, this one side doesn't. If you put the plane over here, just straight on, then one of the deuteriums is going to be pushing into the page, one of them is out of the page. So it doesn't have a plane of symmetry, but it does have rotational symmetry, because if you rotate it again, then this deuterium will start going into the page, and this deuterium will be over here, and it's going to keep going out of the page, so it's going to return to its original self. So it does have rotational symmetry, but it doesn't have a plane of symmetry, so it's going to be here, part 3. Part 3 is going to be option 3, and then by a similar argument, this is going to be option 3. And then looking at the last one, it does have a plane of symmetry, because if you place the plane alongside the plane of the triangle and just have the two deuterium sticking out on the plane of the out of the plane, that's going to be a symmetrical plane because the deuteriums are going to be sticking out at equal angles. So that's your plane of symmetry. And then if you rotate it, then you're going to return to the same result. So if you rotate it like this, it would return to the same result. So it does have a plane of symmetry, and it does have rotational symmetry. So that's going to be number 2. Number 2. No, sorry, it's going to be number 3, and then, sorry, this was rotational symmetry. So this one has a plane of symmetry and rotational symmetry, so it's part 4, and then this option has rotational symmetry but no plane of symmetry, so 3. Very same thing with the equation, so 2 oxidation state of sodium plus oxidation state of silicon plus 6F equals 0, so 2 plus oxidation state of silicon minus 6 is equal to 0, and so silicon is equal to 4 plus 4. So the oxidation of silicon is plus 4. Then what shape do you expect the anion contained for the anion contained in sodium 2 silicon F6? Well, I assume silicon F6 is going to be the anion because sodium with something doesn't seem really that plausible for a cation, and so there's going to be silicon in the middle and then 6 fluorines around it, and this shape is octahedral, so I expect it to be octahedral. For part B, on heating, this decomposes to form a white crystalline solid W and a colourless gas X, which contains silicon. Well, I think that sodium 2 silicon F6 is going to, basically the sodium is either going to chuck out the silicon and a couple of fluorines, or it's going to chuck out a couple of fluorines and not chuck out the silicon. But it seems that a white crystalline solid, a plausible candidate for white crystalline solid, would be sodium fluoride, and in that case we'd have remaining silicon and 4 fluorines, which gives silicon F4, which has a tetrahedral structure and is a gas. Tetrahedral because silicon has pretty much the same outer electron configuration as carbon, and we all know from experience that carbon is tetrahedral. For part 2, formula for W is this, and then X is this, and it's tetrahedral, so that's part 3 now. Give the equation of the formation of W and X from that, so silicon F6 goes to sodium 2 sodium fluorides plus silicon F4. For part C, I'm expecting calcium hydride to react with silicon F4, and so the calcium hydride is obviously going to chuck out the hydrogens and bond with the fluorine, giving me a calcium fluoride, plus still a silicon, still a gas, so silicon can't be in its solid form, so it's probably going to be silicon H4, and balancing this equation gives me this. Then for part 2, combustion of gas Z in air. This is gas Z, so silicon H4. I'm going to treat the silicon just like a carbon, in which case this is methane. Plus O2 gives a silicon O2 plus H2O, and balancing this 2H2O gives me 2O2. And that's it. For part D, we've been told that there is no air in the reaction, otherwise it will combust. So it's going to be silicon H4 silicon hydride, I think that's the name. is straight away decomposes to silicon and then not H2O, so the only other option we have is H2. Balancing gives 2H2, and H2 is indeed combustible in air. For part E, if you just look at the cube here, we have 8 atoms that are at the corners of the cube, and a corner of the cube. If you look at the atom at the corner of the cube, only 1/8 of the atom is going to be in the cube itself. So that's going to be 8 times 1/8. For the corner cubes, the sum of the particles in the corner cubes, then looking at the centers, none of them are on the edges. Looking at the ones that are on the faces, there are exactly 6 of those, and only half of the particle is inside the cube. That's going to be plus 6 times 1/2, plus then those that are completely inside of the volume, of which there are exactly 4. So 4 times 1 gives me 8. When doing these types of questions, and I think judging from experience, there's about 50-50, maybe a bit less chance of a question like this popping up. Just count the ones that are on the corners, count the ones that are on the edges, count the ones that are on their faces, and count the ones that are in the middle. The corner ones have a factor of 1/8, the edges one have a factor of 1/4, the faces one have a factor of 1/2, and the ones in the middle have a factor of 1. Part 2. An expression of the number of atoms in the sphere in terms of A, N, and V. Taking care of units, we know that A is in picometers, so converting A to centimeters, so 1 A times 10 to the 0 in picometers is going to be A times 10 to the minus 12 in meters, and so A times 10 to the minus 10 in centimeters. And so the volume in centimeters is going to be A times 10 to the minus 10 cubed, which is A cubed times 10 to the minus 30. So the total number of cubes is going to be the big volume divided by the small volume, because it's how many small volumes fit in the big volume. So that's going to be V divided by A cubed times 10 to the minus 30, or V over A cubed all times 10 to the 30. And that's the number of cubes. There are 8 silicon atoms in total in a single cube, or N silicon atoms in total in a single cube, giving me a Vn times 10 to the 30 over A cubed atoms in total, give an expression of the Avogadro constant in terms of these variables. Well, we know that the number of atoms is going to be Vn times 10 to the 30 over A cubed, and we also know that the number of moles is going to be the mass of the sphere divided by AR, which is the molar mass of the silicon. And so the Avogadro's number is the number of particles per mole, so dividing the total number of particles by the total number of moles is going to give me the number of particles per mole, so that's Vn times 10 to the 30 over A cubed all over m over AR, which is Vn times AR times 10 to the 30 over MA cubed. Just redraw the larger cube and then draw in the smaller cube. So the smaller cube is here, half of each side length, and it has an atom here, 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 and drawing in the back side. One atom exactly on half of the diagonal, which is half of the diagonal of the small cube, and it's bonded to all 3. So the length of the bond is going to be half the length of the diagonal of the small cube. The side of the small cube is A over 2, so this length of the diagonal by Pythagoras is going to be 3 times root of 3 times A over 2 all squared, because it's root A over 2 plus A over 2 plus A over 2, giving me root 3A over 2. However, that's just the whole of the diagonal, and we need half the diagonal, so that's going to be root 3a over 4 is the length of the diagonal. Part G, that's just a bunch of algebra. I'm going to have the fraction of silicon-29, that's 41.2 times the mass of silicon, so that's 28.9 blah blah blah. I'm not going to write it all up because it's quite long, plus the fraction of silicon-30, so that's 1.3 times 10 to the minus 6. Oh yeah, I forgot to add a times 10 to the minus 6 here, times the mass of silicon-30, so 29.97 blah blah blah, plus the fraction of silicon-28, which is going to be 1, minus the fraction of silicon-29, so 41.2 times 10 to the minus 6, minus the fraction of silicon-30, so minus 1.3 times 10 to the minus 6, all times the mass of silicon-28, and that's 27.976, etc. And this in total should give me something like 27.9769703.1. Part H here, that's just using the formula that we derived earlier. The formula that we derived earlier was AR NV times 10 to the 30 over MA cubed, giving me 27, the answer that we've got here, because that's AR, 27.9769703.1, times N, which is 8, times V, which is given to us in centimetre cubed, 431.059060. Yeah, do excuse the fact that I pronounce numbers really weirdly when I write them down. That's just me reading off the paper, and I don't really do much number pronunciation. Yeah, it's not something that comes in handy in life, I think, maybe. But continuing on, divided by the mass, which is 1008.087559 times a cubed, and that's just 543.09962334. Yeah, 234, no, all cubed. And this gives me 6.0221496 times 10 to the 20.